All right, so first of all, thank you very much for the invitation to this great meeting and for the organizing to putting this together. It's fantastic to be here. And I feel a little bit bad because we've heard great talks about therapies and different approaches, how we're going to tackle this disease, but I'm kind of take you back one step on the preclinical models. So I'm not going to talk about therapies, I'm going to talk mostly about how we are trying to model this disease so that we can develop therapies. The talk is going to be split in two different parts. We're talking about very quickly about the strategy, how we generated this model, and then about an initial characterization of this model. I stole this image. Oops, sorry. I stole this image from a publication from Spela. I think most of you probably recognize that. And I'm not going to discuss this more than just saying that for what we know, the majority of the clinical mutation of the CTNNB1 gene, the beta-catenin gene, sorry. I'm a developmental biology, I used to call it beta-catenin, so I will refer to beta-catenin as the gene, are known are loss of function mutations. So these are mutations that essentially disrupt the function of the gene. So if you want to try to generate a model that recapitulates most of these features, one approach is to try to delete it so that you create really a copy of the gene that has no function. And luckily enough, the Jackson lab had a model that allowed for the generation of this deletion model in its repository, and is this model carrying a conditional allele of the gene. I suspect there are not many mouse geneticists in the audience, so just very quickly, a conditional allele is a normal allele in which two short sequences called LOXP sites have been inserted in intronic regions, which in regions that we think are not really important for the function of the gene. And therefore, in normal conditions, its activity is normal. So a mouse with two copies of this conditional allele will be perfectly normal. However, in presence of a protein which is called Cre recombinase, these two LOXP sites will be recombined together, and the region in between is going to be completely deleted. In the specific beta-catenin allele, 5 exons will be deleted upon Cre-mediated recombination. And we cross these mouse with a mouse model that expresses the Cre essentially in every tissue, especially in the germline, so in sperm and oocytes. So we generate finally a model which carries a deleted gene, which is a pretty drastic mutation of the beta-catenin gene. Essentially, we know that this is a full loss of function gene. We confirm this deletion by PCR and different other methods. I'm not going to go into the details, but what we have now is a mouse line opposite to the line that was presented before, which had a point mutation. This is, I would think, a more drastic loss of function. Now we have a new model, and before you start actually using it to develop your therapies as a model to develop your therapies, obviously, you need to characterize that. And when you have, there is a great book that is called What's Wrong with My Mouse, that gives an overview of how do you characterize. Mice don't talk. This is kind of a drag sometimes because they cannot tell you how they feel and if they have something wrong going on with them. So we did have to choose between different tests, and what we decided to go with is a very, very simple initial characterization where we tested phenotypes that had been already described in a similar mouse, especially the rotarod phenotype. And I'll go a little bit into the details of that, which is a motor function test. And the fear conditioning paradigm, which is a memory, let's say a memory paradigm. The groups are rather small, so we have wild-type groups, these are the littermates, and mutants. We are only testing 12 mice per group, 6 males, 6 females, because we know that sex might actually influence the phenotype of this mutation. And we test the mice at 2 times, at 12 weeks and 20 weeks. The first observation that came out was that the mutant animals, the heterozygous animals, are smaller than wild type. This is more pronounced in males, but it's clearly trend in females. Keep in mind, these are not very large numbers, so if the difference is not huge, you will not pick it up. They do grow, so it's not that they're stunted or the growth is blocked somehow, but it's definitely delayed. And since we do see the difference, as I said, is not huge, it's only about 10% of the weight of the mouse. However, it's very, very, very consistent. So we think this is an initial phenotype that we can see, that it's actually pretty easy to follow. The mice are smaller than the littermates. Well, the littermates. When we measured the rotarod, we saw something interesting. First of all, we don't see a clear rotarod phenotype in females. If you compare wild-type females with heterozygous females, we don't see this difference. And again, sorry, I started with the assumption that everybody knows what the rotarod is. The rotarod is exactly what the name says it is. It's a rotating rod. You put a mouse on a rotating rod, and the mouse will run for his life because mice don't like to fall. And if the mouse is weak or has problems with coordination, it will fall earlier than a wild-type mouse. And we keep them on this rotating rod for 5 minutes, and if they come to after 5 minutes, we take them out. In younger mice, we do see a phenotype. We do see lower performance on the rotarod. This is similar to what has been reported with the point mutation. However, at 20 weeks, we do not see this difference anymore. So it seems that the phenotype, at least, is definitely not getting worse, but these mice seem to recover over time. The fact that the mutant mice seem to perform better, I would probably say that it's due to the fact that these are small groups. You see that there is a wild-type mouse here that probably didn't want to run that day, so fell down early and kind of skewed everything. I wouldn't put too much weight on this difference, even if it's statistically significant. But the take-home message is there might be a motor function phenotype. It doesn't seem to be progressive. The second test that we run is fear conditioning. I mean, fear conditioning is kind of a scary name. And what we do is we take a mouse and we put it in a cage that is very clearly for him to recognize. For example, a cage with a red wall and a yellow wall, something that he will recognize very easily. We let 3 minutes the mouse in the cage, and then we startle it with a sound, a very strong sound. And then a foot shock. There is a grate with electricity, and we give a mild foot shock, but still unpleasant. Let it rest for a minute, and then we repeat the procedure. So the way this thing works is exactly the way that the soundtrack of Jaws, the Steven Spielberg movie, works. So the first time you hear it, something very bad happens. The second time you hear it, you're already waiting for something bad to happen. So it works more or less in the same way. Because what we do the day after, we take these mice that have been trained and we put them in the same cage And we don't do nothing. We just look for freezing, which is an expression of fear in the mouse. So we leave them for 5 minutes, and they will recognize the cage, and they will freeze because they're scared that something bad will happen to them, even if we don't do anything to them. Then we take them out, and 1 hour later, we put them in a different cage, so they will not recognize the cage, but they will actually recognize the tone, because we play the tone. And if they remember that after the tone there is a shock, they will freeze more. The results were quite interesting. Again, I'm showing first the females and then the males in this case. You see that both the mutant and the wild type did learn fear conditioning. That's the baseline. Then after the first shock, they start freezing more. After the second shock, they start freezing. And this increase is what you normally see in fear conditioning, because the mouse is learning what's coming. The day after, we took the mice and we put them in the context, so in this cage. And you see that heterozygous beta-catenin null females, they freeze more. Then they go back to baseline if you put back into a cage with no contextual fear. But then when you play the tone, again, they seem to freeze more. And this is just the same data plotted in a different way. I'm just glad my graphs show. We repeated this experiment at 20 weeks. The previous one was 12 weeks of age. This is generally something you don't do because these mice have been preconditioned. So the second test is expected to be much more noisy because mice will remember what happened 8 weeks ago, more or less. It was just to see if we could reobserve the same trend, and indeed we do. We do see that female heterozygous for the beta-catenin null allele tend to freeze more than wild type. What about males? Males seem to have a slightly different phenotype. During the learning phase, these guys learned very quickly what was coming to them, and they froze more than the wild type litter mates. However, in the context and acute fear analysis afterwards, we didn't see a lot of these or any major difference. So there seemed to be an effect on sex on the phenotypes elicited by the beta-catenin deletion. And what we can say after this initial test is there doesn't seem to appear any major memory deficit in this model. These mice remember exactly what happened to them, but they seem to be somehow more sensitive, either to the shock or to the environment. So there is something there, although it's different between the males and the females. So that's just a conclusion, and I want to stress the fact that this is an initial characterization. For practical reasons, timing reasons, we had to use very few mice, small groups, and so on and so forth. So all these data need to be taken with a grain of salt. But I would say that we definitely see, it's not really a decreased growth rate, but I would say a delayed growth rate in both sexes. It's more evident in the males, but that's probably because males are usually heavier than females. Then we do see motor performance phenotype in males, but at a younger age. This doesn't seem to get worse, actually seems to recover over time. And finally, we do see increased sensitivity to the fear conditioning test. And again, these effects seem to be depending on the sex. And with this, I will actually thank you all for your attention, and I will let the podium to the next speaker.